Welcome students. In today's class we are going to learn about some heuristic based scheduling, specifically the lease scheduling for MLRC problem. So, if you remember that this scheduling where we are going to assign time step to the operations is in general NP complete problem, and the primary reason of this problem is that once you try to schedule say certain operation at certain time stamp, say you are trying to schedule the operation in time step 1 and say the number of resource available is k and there are more than k operations is available to be scheduled in that time stamp, right. And since there is you have to just select a subset of the operations from this available set, and selecting this subset greedily at that point sometimes is not possible, because the choice that you are taking is may not be guaranteeing to have an optimal solution, right. That is why this problem is NP complete, right, in general. Then in previous class what we have seen, that is we take certain assumptions and under those assumptions we have seen that particular scheduling problem become polynomial time solvable. And what are those assumptions? So, we assume that all operations are of same type. In general, your the sequence graph has operations which is addition, multiplications and so on, and now in this particular multiprocessor scheduling we have seen that we can have a single type of function unit which is a processor, multiprocessor, which can execute any operations, right. So, you are assuming that all nodes of same type, then you assume that all operations of unit delay, the delay is 1, and specifically this sequence graph is a tree, right. The data dependency graph that we have given is tree. That means from any node you have exactly one path to the sink node. So, at that point, because there is no multiple paths or there is no multiple possibilities to reaching the sink node, so for this particular cases where this assumption 1, 2 and 3 holds, you can have an algorithm which can select that subset that I am just talking about, that you have say n number of operations available in a time step and you have to select k. You can select a subset based on those nodes distance from the sink node, and that guaranteed that particular solution will result in minimum number of latency to schedule those operations. And this is what we have learned in the previous class, and we have seen that the Hughes algorithm that actually exactly done that. And specifically that important thing is that the distance. So, we are actually leveling the nodes with a distance from the sink node, right. And what is that? So, is basically talked about distance from the sink node, and that particular distance is important because if you just think about this node, so in a separate time stamp 1 there are 5 nodes which is available to be scheduled, because they are depends on the inputs, and say suppose I have to select 3, I should select the nodes that has the maximum level. So, I am going to select this one and this one, because this node delay is 4, that means there are 4 nodes still to be scheduled following this node. Similarly, it is 4, there are 4 nodes to be scheduled. For this node there are 3 nodes to be scheduled. So, for this node 2 nodes to be scheduled, for this node 2 nodes to be scheduled, right. So, if we select the node that has higher level, that means I am actually making sure that there are many other nodes that are yet to be scheduled, they will become available earlier, right. So, as a result this will ensure the schedule which is minimal, right. So, that is something we have understood in the previous class. So, now for generic graph where the path is not unique, specifically the assumption 3 that this is tree does not hold, and also your operations can have a different delay, and then you can have different type of operator. So, this is the generic graph. In that case you may not, there is no way you can have a polynomial time algorithm which can give you optimal solution. So, what is usually is taken care is a heuristic based approach, right. It is basically some kind of approximation you are doing, so that you which is basically more logical in the sense, right. So, the point, for example, say what about just applying this Hughes algorithm for this kind of graph, right. So, which is also making sense. This may not be give you the optimal solution in some corner cases, but most of the time this is a logical assumption even for a sequence graph which is a graph, not a tree, right. That if so among the operation that is available to be scheduled, I am going to take operations which has higher level, right. For example, say in this example, suppose these are the nodes are available to be scheduled in a time step 1, and if you see here for this node the distance is 1, 2, 3, 4, 5, 6, right. So, it is 6 for this node 1, 2, 3, 4, 5, 5 for this node 1, 2, 3, 4, it is 4. So, 6, 5 and this is 3, 1, 2, 3, right. So, basically obviously here you can see that you can actually choose, if there are 2 FU available, you should select these 2, right. So, so basically for this you can actually apply the same logic and most likely this will work, because in the same logic holds here that the distance this if you select this there are many operations yet to be scheduled in distance. So, it will actually help, right. But in some cases, like for example, here if you have say 5 operation now ready to be scheduled in say timestamp 1 and you have say 2 operator, see here for all node the distance is 3, right. So, you can see here the distance is 1, 2, 1, 2, 1, 2. So, there are many paths from this node, there are many paths, 1 path, 2 paths, 1 path from this node, there are 1 path from this node, 1 path from this node, there are 2 paths and so on, right. So, this is not definitely not a tree, but what I am try to say that here because all node the level is 2. So, that particular logic so here is a problem, right. There are 5 nodes which has the level 3 all have leveling 2 and you try to select only 2 of them. So, which one to select, right. So, this is something you have to select arbitrarily, and specifically if you choose some arbitrary one that may not give you the optimal solution. So, that is why this particular Hughes algorithm is not directly applicable for generic graph, because basically this choice may not be unique and the choice that you are going to make may not guarantee to give you a optimal solution. For example, here you just try to look into this problem closely. So, for example, say for this node it has only one output, right. For if you try to see that from this node there are many paths, 2 paths, right. So, probably among these 2 I am going to give preference to this node, right, because this if you select this there are 2 other path nodes are have the dependency is now resolved. So, those nodes are now will be ready to be scheduled in the next subsequent step. So, this kind of logic might come as a secondary decision making, right, but again that may not always hold for any time. So, this is what is the heuristic that I just talked to you, right. So, the first heuristic that we talked is among the nodes you select the node which has the highest number of level or the priority. So, which holds perfectly for here, but if you as I mentioned for this, since all the node has the distance from the sync node is 2. So, obviously that particular logic will take arbitrary one and that arbitrary may not give you the best solution. So, what I just argued that maybe you can have a heuristic 2 is in this case if there is a collision I am going to select the node which has from that there are more has more paths than the other one, right. So, that is something is my heuristic, but it may work for this graph, but it may not work for some other kind of graphs, right. So, heuristic is something like that. So, specifically the heuristic approach whenever you have more choice, right, you have to select a subset from a set of nodes, you have to have some priority, right. You must have some priority, you have to decide on those nodes and based on the priority you select subset. So, your algorithm will be faster because you are just going by some priority rules and you just select them. So, the algorithm will run in very fast manner and that priority must be sensible enough, right, that is the way I explained here. So, and that particular priority may give you good solution or near optimal solution in most of the practical cases, maybe some corner cases it may not give you the optimal solutions. And I am happy enough because I am not going to run for 2 to the power n number of complexity, rather I can just run in order of n or say order n log n kind of complexities, right. So, this is what is the heuristic approach, right. So, in nutshell that you give a you assign a priority to nodes and whenever there is a collision you have to select a subset from this, you actually apply this priority and based on the priority the nodes has the highest priority you pick them, right, and this priority can differ, right. So, you can have your own priority and you can prove that that priority is something works for many scenarios, right. So, that is the overall idea of the heuristic based approach, and one of this most important heuristic based approach is called lease scheduling, right. And what is this lease scheduling? It is basically the generalization of the idea of Hughes algorithm. So, it is basically take the same idea of heuristic of the Hughes algorithm which has applied for multiprocessor scheduling, but let us say I am going to apply the same logic to a general sequence graph where you do not have the assumption 1, 2 and 3, right. So, that is what is called least scheduling. So, it is a heuristic approach which is inherited the idea from the Hughes algorithm, and it is basically generalized the some of the aspect of the Hughes algorithm, so that it is actually getting applied for generic graph, right. So, obviously, as I mentioned that its complexity is very fast, is just like Hughes algorithm, and since it is applicable to generic graph, it can work for multi-cycle, pipeline or different type of resource. So, all kind of flexibility it has, and we can have both the versions. We can have the least scheduling for minimization of latency under resource constraint or minimization of resource under latency constraint. So, both is we can have least scheduling, and we are going to learn this too. In today's class, we are going to learn this, that I have resource constraint is given, I have given the resource bound, and I am going to identify the minimum latency using the least scheduling. Okay. And as I mentioned that for any such heuristic algorithm, you need a priority logic, right, and in this particular least scheduling they apply the same logic whatever is given in Hughes algorithm, which is the longest path to the sink. So, here because in that Hughes algorithm, because it was a tree, you have always a one path, you can always say the distance from this node from the sink node, because it has a one path, but in generic case, for example, for this graph, this is a generic graph. So, for this graph you can see here, so from this path there are how many paths? This is one path. So, this is one path, this is one path, right. So, you can see here the distance of this node is 1, 2, 3, 4, 5, 6. This node is 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So, this is 5, this is also 1, 2, 3, 4, 5. So, 5. So, there are 3 paths, and one of the path distance is 6. So, I will assume that for this node the distance from this sink node is 6, right. So, instead of, so in Hughes algorithm we have seen that we have taken a level which is basically the distance from the sink node, because it has a unique path. Now, you have multiple paths. So, I am going to take the path which has the maximum distance. Okay. So, this is what this least scheduling consider as the priority, right. I hope you understand that. And now, so as I mentioned, there are two type of algorithm, either you do this for minimization of latency under resource constraint, or you do this minimization of resource under latency constraints. So, there are two type of resource. So, today we are going to learn about this algorithm 1. Okay. And so, if you remember that in Hughes algorithm, so we have a level, and and basically since all the nodes are of unit delay. So, if it is scheduled in say time step L, it will complete the execution in time step L only, right. But in general the nodes can have multiple delays. So, if the nodes schedule in time step L, it may continue for 2 cycles, 3 cycles or many cycles based on the type of a node. So, this may be multiplier, this may be adder, this may be divider and so on, right. So, that the delay may be more, right. So, in Hughes algorithm we just if I schedule them here we are done, but in least scheduling we have to check if the operation is start its execution in time step L till what time it is running, right. So, only if when it is complete its execution, its subsequent node will be ready to be scheduled, right. So, so that is something we have to understand. So, there are two type of things we will understand, the candidate operator and unfinished operator. I am going to explain them in detail here, and also we have a priority list that I have already explained, that it is from the, for any node it is the longest path, distance of the longest path from the sink node. Okay. So, let us try to understand the candidate operator. So, as I mentioned here, you have not a single type of operator, right, you have many type of operators. So, let us say I am going to take a operator of type k, right. So, this k can be multiplier or adder, right. So, now for this type k, what I am going to identify this is the candidate operator, that means this operation can be scheduled in time step L. So, I am actually talking about a time step L, right. So, when this particular an operation is ready to be scheduled in time step L, when so this node all the predecessors, say that it may be 3 predecessors, right. So, it may say one predecessor here, one predecessor here and one predecessor here, right. So, when these operations will be scheduled? So, when all the predecessors are completed their executions. So, that means if there is an edge, so suppose this node is Vi and its predecessors are Vj. So, this is Vj, say this is also Vj1, this is Vj2. So, this is basically for all type of all predecessors, right. So, when this particular node will be available, when all of them are done, right. So, now if you assume that this Tj is the start time of this node. So, Tj and the delay is Dj. So, this must be greater than that means this is already done, right. So, Tj plus Dj. So, it is started from this time step Tj and it will complete the execution here in Tj plus Dj minus 1. So, from Tj plus Dj I am ready, right. So, this Tj plus must be less than equal to L, right. This is what the rule, and this is true for all j, right. This is for all j which is the predecessors of the current node. In high level, I have to see what are the nodes are the predecessors of this node, or this node Vi depends on what are the nodes previously, and I have to make sure that all the previous nodes already completed their execution, right. So, that means now I can schedule Vi. Okay. So, I am going to take those such node and I am going to put in ULK, right. It is in for time step L, time step L and operator type K. So, I have to do it for all such time step and for all stuff operator. Okay. So, this I am going to do. So, that means it is basically similar to that U in the Hughes algorithm. So, in the U we have that unscheduled operations whose vertices have already predecessor vertices are already scheduled, right. So, that means since earlier cases it is the predecessor has a single cycle, if it is scheduled means it is completed in that time step itself, right. So, this is basically we do not have to do it for the type of operator, or you can just think about this is L for each time step, right. So, this is what is this candidate operator, and the next set of operators is the unfinished operator. So, suppose you are as I mentioned earlier that if you have, because this operator can be multi cycle, so suppose you have started this operation from this time step Tj, right, and it is running, right. So, you are now in time step L. So, it must be if it is not completed, then say suppose this is your L is this. So, that means this operation is running in this time step. So, I need a resource for that, right. So, this is called unfinished operation TLK, again for that operator type K, and in time step L those operations of type K that have started earlier cycles and whose execution is still not finished at time step L, right. So, if this operation is started here and it is still going on, so in L this is running. So, this operation will come into TLK, right. So, so that means here all the nodes which type is K and it is Ti plus Di, its running time is still greater than L. So, that means it is still running, it started here Ti and still going on, it will complete here, but I am here, right. So, that means these are the sets which has to be, we need to allot resource for these nodes definitely in time step L, because these are all running, I cannot stop them or halt them in between, right. So, this particular things was not there in the Hughes algorithm, because there it is basically one, all operations were single cycle, right. So, these two important information, the candidate operation is that means the operation which is now ready to be scheduled in time step L, and the unfinished operation, that means these operations started its execution earlier and it is actually running in time step L. Okay. And the priority list, as I mentioned, that you can actually for each node you identify the distance of that node from the sync node by identify the longest path. You might have many paths, but you identify the path which is the longest among all the paths, right. And then you actually assign the value to those nodes, okay. And then you can actually sort the nodes based on their level, okay. So, it is basically again I am leveling with the distance of that node from the sync node, and I am going to go, if there are multiple paths, it is the longest path I am going to consider, okay. So, these are the three informations, let us say I have available now. Then this list scheduling is very simple. It is very similar to your Hughes algorithm, and let me try to explain, and it is for MLRC. That means, I have resource constant is bound is given. So, I have given a resource bound which is a vector. So, A is basically A1, A2, A1, A2 to AK. There are k type of resource. So, this is the resource bound for each type of resource. So, what I am going to do? I am going to do the things for all nodes in my sequence graph. So, I am going to run a outer loop until my all nodes are scheduled. So, Vn is the sync node. So, until my sync node is scheduled, I am going to do this whole process time and again, right. And then what I am going to do? For each type of resource, I am going to do the things, right. So, it is for each type of resource in each timestamp. So, you can see here I start my timestamp with L equal to 1, and I am going to increase this timestamp to this. So, that means, this particular loop actually doing the scheduling in timestamp L. Once the Lth timestamp is over, I am going to move to the L plus 1. So, it is basically I will start my scheduling of timestamp 1, then I am going to do it for timestamp 2, then timestamp 3 and so on, right. I am going to do it and until my sync node is scheduled. Okay. So, what I am going to do it here? So, I am going to identify for each type of resource k, I will identify the candidate operations which is ready to be scheduled in this timestamp, and that I have already explained that means is for these operations predecessor, all predecessor on which this operation depend have finished their execution before L, right. It is not running in timestamp L. So, that is my ULK, and this TLK is something is the all the operations that have started early, but still continuing, it is still running in timestamp L, and those operations of type K, right. So, this is already I have identified the unfinished operations, and then I am going to I am to make sure that I need resource for this, right. I cannot avoid this. So, I must have to allot resource for TLK, and if still some resource available, then you select a subset from this, right. You select a subset from this and assign to this timestamp, right, because suppose you have say AK. So, if you say as your this is a multiplier and there is a 3 multiplier, and this TLK is 2 and this is say 3. So, that means there are 3 multiplier is ready to be scheduled in this timestamp, and 2 is actually have started early and it is still continuing. So, that means now I must, and there are say 3 multiplier available, I must allot 2 multiplier to this, and since I have 1 multiplier idle for this state, I can select one of these available operations and I can schedule them in this timestamp. Okay. So, now this selection is the based on the priority. Okay. So, now in this particular class I am just assuming that this is the priority based on the longest path distance from the sync node, but you can have different priority, you can have say some very complex priority. So, that is why this algorithm is very generic. It just say ki you select a subset from this available operations such that you do not overshoot the resource requirement, right. So, that is what this sentence means, but selection is based on the priority, and that is where you can apply different heuristic, different priority, and you can select those operations which has the highest priority. Okay. And once you select this subset of nodes which is can be scheduled in timestamp L, you just schedule those operations into timestamp L. So, that means I am going to do it for each type of resource, resource A1, then A2, A3 to AK. Once I have done for all type of resource in timestamp L, that means my L scheduling for L is done, I will move to the L plus 1 timestamp. So, that is what I am doing here. I will just increase the timestamp and I will go to the next timestamp, and again I am going to calculate the ULK and TLK. You remember that based on your choice here, this ULK and TLK you have to calculate, right, because you based on the operation that you are scheduling in previous timestamps, your ULK and TLK it is not fixed for each operation, because L is it is increased here. So, this ULK, that means it is, if it is for the timestamp it is U1k, in timestamp 2 it is 2k. So, you have to recalculate this based on the operation that was running now, whether they have finished the things or not. If finished, those operations will move from TLK to ULK. You understand, right? So, this is what is this whole process, and this can be done very efficiently, and it is very fast algorithm, and the important point is that it actually works gives good results for most of the kind of sequence graph, and importantly this particular algorithm is widely applied for any commercial high level synthesis tool. So, that is why it is a simple algorithm, but this is what is getting applied in practical high level synthesis tool, because this is fast, and most of the time if your priority is basically the longest path, most of the time it gives you good solution. And now actually you can change this priority. Suppose you want to do some reliability things bring into picture, you want to bring say some power consumptions bring into picture, you can actually change your heuristic, right. So, or say you want to do that, so you have some aware of the interconnections cost and so on. So, you can actually think on that, you can actually add those kind of logic into your this priority list. So, the beauty of this algorithm, it is a very generic algorithm, and based on your applications, based on your optimization objective, you can set your priority and based on that your algorithm will work, right. The basic logic will remain the same, but you can apply different heuristic just to get your different objective fulfilled. Okay. So, what I am going to do it now, I will just try to compare with the Hughes algorithm. So, you see here, so this is your ULK basically, you are selecting ULK because there is no K here, it is UL because it is the one type of operator. So, you can assume that UL 1 because it is K is always 1. So, that is why this inner loop is not there. You can see here I have an inner loop because it is for each type of resource. Since I have only one type of resource, this for loop will run only once. So, that is not there, right. So, you can see here, so there is no inner loop, but the outer loop is there. So, it is basically doing for timestamp 1, timestamp 2 and timestamp 3 until I finish my last operation. So, you can understand that this is basically just the generalization of the Hughes algorithm for generic graph, where I just added a for loop here which actually run for different type of resource, which is not there in the Hughes algorithm because it is only one type of resource, and I am doing exactly the same thing because I am just there also I am just identifying the that operation that is ready to be scheduled. Here also I am identifying the operation that is ready to be scheduled. In addition, because the operation is multi-cycle, here I am identifying the operation that are running here which is not needed here, it will be always 0 here, right. So, the T L will be always 0 here because there is no operation. If it is scheduled in timestamp L minus 1, it will finish the execution in L minus 1, it will not go to L in timestamp L, right. So, that is why this TLK is not there, but I am just adding it here because it is needed for generic cases, and I am doing the same thing here. Then the next step is you select a subset. Here also you are selecting a subset, but there since there is by TLK is 0, you just select a subset so that your resource bound is met. Here I am doing the similar thing, I am selecting a subset, but I am making sure that I have enough resource to run the allocate resource to the running operations, and then only you select this subset. So, exactly the same thing what is happening in Hughes algorithm, it is happening here also, only thing I am just making it is a generalized for general purpose sequence graph, right. So, one question you might have things, how do you ensure that the running operation is always less than AK, right. This question might come to your mind, right, because I am doing it from L minus 1 to then L minus 1, right. So, you are doing in L minus 1, then you are doing in L. So, how do you ensure that when you are doing in timestamp L that the number of running operations must be less than AK? You might have a situation where you cannot select any new operation because the running operation is equal to the AK. So, but how do you guarantee that it does not go beyond AK? Because you are already this formula satisfied for timestamp L minus 1 as well. So, that means for the timestamp L minus 1, the number of running operations plus the operation you are added, that is less than AK, and those operations at max can run in this timestamp, right. So, whatever your S K plus T L K minus 1. So, this was the operations you were running in L minus 1, right, and this will become your T L K at most. Since this is less than equal to A K, so this also must be less than A K, because in a timestamp L minus 1 I have made sure that the number of running operations at that timestamp plus the new operation I have added, that must be less than equal to A K, and those are the operation at most can still running in L. Few of them may be complete, but at most this all may be running in time step L. So, this way I am actually ensuring that in every time step whatever the running operations, they are always less than equal to the number of resource available. So, it will not go into another that scenario anytime. Okay. So, I will just move on. What I am going to do it now, I am going to take couple of examples. I am going to show that how this MLRC, list based scheduling, works. Okay. So, first I will take the same example, so which is basically tree. So, for this Hughes algorithm also applicable, only thing is that here I have a different type of operator. I have plus, minus, multiplication, everything. Okay. So, and let us assume that I have two type of resource, one is multiplier, I have multiplier 2 and ALU is 2. Okay. So, 2 ALU which can execute plus, minus and greater than, less than operations. Okay. So, let me try to understand, explain this, and I assume that all these operations are one cycle. So, this is the simplest possible cases. So, I have all operations of single cycle. So, what I am going to do? In the step 1, so every time step you have to identify the U, the available operation ready to be scheduled, and TLK. For time step 1 there is no T because there is no running operation because you are in time step 1. So, you can identify and this you have to do for each type of resource. I will do for multiplier and then I have to do for ALU. Okay. So, you can understand that in time step 1 there are these 4 operations are ready to be scheduled. So, V1, V2, V6 and V8, and since I have 2 multiplier available, so which I am going to select, which is the distance highest distance. So, in this case this is, you remember that this is 4, this is also 4, this is 3, this is 3, right, 1, 2, 3, 1, sorry, this is 2. So, obviously I am going to select this 1 and 2. So, that is why I have scheduled 1 and 2 in time step 1, right. So, this I have done. Similarly, in the first time step only these operations is available for the ALU type operations, only one available and there are 2 resources, I am going to schedule it. So, that is why I have scheduled V10. So, this is my time step 1, and since this there is no this all operations are single cycle, TLK is always 0 because there is no operation is carry forward to the next time step. So, this is the simplest scenario. Okay. So, in time step 2 what I am going to do? So, that means I have already done the scheduling of this 3 in time step 1. So, in time step 2 what are the operations available? This node 3, 6 and 8. So, 3, 6 and 8, and this distance is 3. So, this is the distance is 3 from the sync node, for this node sync distance 3 and this is 2. So, I am going to select 3 and 6 because I can select at most 2. So, I have done 3 and 6 here. And for ALU now I am going for the next type of operator. So, these 2 are done in time step 2. Okay. And for ALU operations still this operation, only this operation is available now because the other ALU type operator is still not available because their predecessors are not scheduled yet. So, there is only one. So, I am going to schedule this V11 in time step 2. Okay. So, in time step 3, so you can understand easily now the multiplier available is say this and this and this is also 2 and there are 2 available and 2 multiplier available. So, I am going to select schedule both 7 and 8 here, 7 and 8. And for this ALU type operation, since this was done earlier, so this is available and only one available. So, I am going to schedule that. So, this is my schedule in time step 3. So, in time step 4 I have, there is no multiplier. So, there is no multiplication operation. So, that V U 1 4 is 0, right, V 4 it is basically LK, right. So, L 1 is 0, there is no operations, multiplication operations, but there are 2 ALU operations, this and this, and there are 2 resource available. So, let us schedule them here. So, this is the schedule I am going to get for this particular constraint, and you and it can schedule in time step 4 with 2 and 2 resource. So, remember whenever we discuss the ILP so ILP solution, so I got the same solution. So, this is 4th timestamp, and if you remember this is for this example the minimum lambda mean is equal to 4. So, you cannot schedule this behavior less than 4th timestamp when all operation is single cycle, and we have already discussed that. So, for So, if you have this 2 with this my logic, my MLRC can actually give you the optimal solution. So, this is all solution I am going to get it if I run the ILP also for this problem with resource constant 2. We have already checked that, you can actually cross check. So, that is why I am saying that lease scheduling may give you good solution, best solution sometime if your structure like this, but it may not give you the best solution, the optimal solution all the time. Okay. So, let me take the same example, but now I assume that the delay of the multiplier is 2 and my resource bound is 3 1 not 2 2. So, I have 3 multiplier 1 ALU, okay, 1 ALU. So, let me try to solve the problem again. So, you can understand that the first time step, the multiplier available is 4 multipliers are available and their delay is 4 4 3 2 and I can select 3. So, I can obviously going to select 1 2 and 6. So, I have done 1 2 and 6, right, and this ALU operation 1 is available. So, I just schedule ALU 1, right, this is what I have done. So, this is what I have done in timestamp 1. Okay. So, this is not scheduled yet, this all 3 done. In timestamp 2, my T is V1 V2 because these are 2 cycle operations. So, they are going to be running, right. So, there are my T 2 1 equal to this, right. So, V1, V2 and V6, and although I have V8 and then that U21 is V8, although I have 1 operations available, but I cannot schedule because I have 3 multiplier, all 3 are occupied by my running operations. So, I am not going to take any new operation in this timestamp. So, that is why I have not, see here I just do not schedule a new multiplier in timestamp 2. So, all these operations are running and they are occupying my the multiplier, and since there is no although there are some operations ready to be scheduled like V8, I cannot schedule them because the resource multiplier resource are already occupied. Okay. But I can always schedule this V11 which is basically single cycle operation. So, this is only new operation schedule in this timestamp is V11 and these are all running. In timestamp 3 these all are done, right, these all three are done because they are already completed their execution. So, for now let us identify that. So, now whenever they are done, my U is U 3 1, that means in timestamp 3 for type multiplier 1, my V 3 then V 7 and V 8 are available. So, I am going to schedule all of them in timestamp 3 because 3 multiplier available and 3 only resource, I do not have to check the priority, I can schedule them. Okay. And there is no such ALU available because ALU is blank because there is no operation is ready to be scheduled. So, I am not going to do anything here. So, in timestamp 4 it is very interesting that my these 3 operations are running. So, I cannot consider any new multiplier and still there is no other operation getting finished. So, none of the ALU operation is ready. So, I did not schedule any ALU operation in timestamp 4 as well. Okay. So, in timestamp 4 only these 3 multiplier running, no new operation is scheduled in timestamp 4. In timestamp 5, so this multiplier is now done. So, now these 2 ALU operations are there, but there is no multiplier. So, now the multiplier will remain idle for the rest of the timestamp. Although there are 3 multiplier, they are all been used only till timestamp 4 because there are 6 multiplications and they are all completed till timestamp 4. So, from timestamp 5, 6 and 7 for the rest of the execution this multiplier will remain idle, they have no use. Okay. But in timestamp 5 you can understand that this this V4 this operation 4 and 9 is ready to be scheduled, but which one I am going to select because this distance is 1, this distance is 2. So, I should select this V4. So, I have selected V4 because I have only one ALU available, right. So, I just schedule V4 here, and in the next time step again V5 and V11 are available. I can select any of them because both have the distance 1 from the sync node. So, let us say I have selected V5 and in the next time step I am going to select V9. Okay. So, this V9. So, what I got it here. So, with 3 multiplier which is 2 cycle operations, multi cycle operation and 1 ALU, I need 7 latency is basically 7, right. And if you just assume this latency is basically lambda plus 1 is basically 8, but I need 7 cycle to complete this execution. Okay. So, this is for multi-cycle operations. Now, let us take the same example. I am going to quickly finish this, that now you assume that still I have 3 mult and 1 ALU. So basically that 3 1 still available, but this is 2 stage pipeline. Okay, this is basically 2 stage pipeline multiplier. So, what is the difference between multi-cycle and pipeline? So, in the 2 stage the pipeline where I can actually run them, I can actually insert the next set of input to the same multiplier, because it has 2 stage. So, basically just to finish, so if this is the multiplier, it has 2 stage, I have a pipeline here. So, what I am going to do, it is basically in the first clock I am going to give say A1 and B1, right. So, this is A1 and B1. So, it will do the multiplication and it will put the intermediate results into this, say this, which is basically say R1, and in the next clock I am going to give A2 and B2. So, this part of the multiplier will work on the A2 B2, and this part of the multiplier will work on A1 B1, because that intermediate results is stored in R1. So, it will work on the R1. So, that means when it has multiple stages, and different stage can work on different stage, different set of data. This is very standard pipeline logic. So, if I apply this concept here, so what I am going to do it, you can understand that in first timestamp there are 4 multiplier available, and you know their distance is 4 4 3 2. So, I am going to select this 3, which is similar to the previous one, that 1 2 6. The interesting point, and for V10, because this is available, I can schedule it here, there is no problem here. So, you closely look into timestamp 2. Okay. So, in the timestamp 2, if you so basically I have already scheduled these nodes. So, how many multiplier are available? So, U21 is basically V8. I have one of multiplier can be scheduled, and since this multiplier are pipelined, so what I can do, I can just start this execution and I can pipeline any of the multiplier where these 2 are running, let us say V6 and V8. So, that means now these 2 multiplier is basically the same multiplier, which is so here this will work on the data for V8 and this will work on the data on V6, right. This is what is the beauty of this. So, this is how we can actually do the pipeline things, and in the next timestamp, so these operations will finish. So, now I can actually assign, so this is maybe multiplier 1, this is multiplier 2, this is multiplier 3, this is also multiplier 3, because these are pipelined. In the next timestamp, when these 2 operations are done, what I can do is basically my 3 7 is available. So, I can put, and also 8 is available. So, I can just put, because 3 and 7 has the highest length, the priority. So, I am going to run them again. So, this again will run on multiplier 1, this is on multiplier 2, still multiplier 3 is running, right. This is how I will do it, and so the availability of the multiplier here is all 3 actually available, right. So, in this timestamp all 3 are available. If there are 3 multiplication operations are there, I could have start their executions by the pipelining that with the existing multiplier, which is already running on the different set of data. Okay. So, that is the concept. If you just do it, you can actually execute the whole behavior in 6 timestamp, lambda equal to 6. So, with the pipeline version with same type of resource 3 and 1, I can execute this behavior in 6 clock. Okay. So, that is what is the pipeline version of this example. I hope now this lease scheduling is very much clear to you, and you must appreciate that this is something very fast algorithm and actually can give you good results for most of the scheduling problem for generic sequence graph. Okay. So, with this I conclude today's class. In the next class I am going to discuss about the same lease scheduling for the minimizations of resource under latency bound. So, that particular problem. Okay. Thank you.